So we've investigated and looked at momentum. Now it's time to look at change in momentum. Well, let's first just look at the formulas we mentioned before. Previously, we already said that a change in momentum is going to be due to a change in either the mass or the velocity. It could be a change in velocity, which is the most common type we see. It could be due to a change in mass with constant velocity, or it could be due to a change in mass and a change in velocity. Change in momentum is, of course, also equal to the momentum at any instant in time minus the initial momentum. So those are our two relationships here. Now, when it comes to units, let's suppose I have 5 apples and I give away 3 apples. I end up with 2 apples. I don't end up with 2 oranges. I don't end up with 2 limes. I end up with 2 apples. So if I have a momentum and I subtract another momentum, the units will be momentum. So the units for all of this are going to be kilogram meters per second. If I have a velocity of 5 meters, if I have delta V is V minus V0, and I have an initial velocity of, let's say, 4 meters per second, and afterward my velocity is minus 2 meters per second, well, then I have minus 2 minus 4, which is going to give me minus 6 meters per second. The change in velocity is a vector quantity. The velocities are vector quantity. The change in velocity is a vector quantity. And since momentum involves, a change in momentum involves a change in velocity, the change in momentum will also be a vector quantity. So it is a vector, and the units will have the same, will be the same as momentum, as with all things. All right, let's do a calculation here. We have a collision with a wall. We have a ball. And looks like we have an east-west situation. So east positive, west negative. It's moving 6 meters per second west. So here's the ball. Moving 6 meters per second west. So the V0 is minus 6 meters per second, because west is negative. Collides with a wall. So that wall will be like this. And it bounces off without a change in its speed. So its speed will be the same. So afterward, the velocity will be 6 meters per second. The collision lasted for 0.20 seconds. What is the momentum before? So the initial momentum, P0, is going to be mv. And the mass is 1.000, and the velocity was minus 6.0. So we end up with minus 6.0 kilogram meters per second. That is the initial momentum. 2 significant digits, 4 significant digits, my answer is with 2. So before the collision, well, what is it afterward? Well, the instantaneous momentum then, 1.000, and the velocity is now 6.0. So the momentum afterward is 6.0 kilogram meters per second. What is the change in momentum? The change in momentum is P minus P0. So we have 6.0 minus a negative 6.0, which is 12 kilogram meters per second. Let's see, was the momentum positive, the change positive? Yes, it ended up positive. It had negative, it was brought to 0, and then ended up going positive. So the change was 12. Now we could do this as delta P is m delta V, and the mass is 1.000, and delta V, let's see, is V minus V0. So the final velocity was 6.0 minus a negative 6.0, which gives us 12, or 12 kilogram meters per second. Both give us the same answer. Well, what about the rate of change of momentum? The rate of change of momentum is just this, is that thing divided by the time. And so we have a change of momentum of 12, and we're told it occurs in 0.20 seconds. Which is 60. kilogram meters per second, which gives us kilogram meters per second squared. Another way we could look at this rate of change of momentum would be to look at this, m delta v, because change of momentum is m delta v over delta t. And when you look at this delta v over delta t, you can see that's ma. Thus, the unit's kilogram meter per second squared. So this delta p over delta t is equal to mass times acceleration. Oh, delta p over delta t equals ma. Wonderful. And so that's how we would compute our rate of change in momentum.